Good afternoon, my name is Iara Oliveira, and today I'm going to present the work called Estimation Method of Fatigue Properties from Hardness Measurements of an Ancient Iron Bridge. So here are the main contents of this presentation. I would like to start mention the Mason-Coffin-Baskin equation for strain life curves. Here you can see the equation, it's a famous equation. And after the development of these equations, many other estimation methods were developed with already predefined coefficients. And for different types of materials, we have for high alloy steels, low alloy steels, titanium alloys, aluminum alloys, but we don't have any estimation method for Asian materials. And why is that important? Because we have many structures all over the world that we are still using, especially bridges. They're made of this type of material. So here, what we're trying to do was trying to estimate fatigue properties from hardness data. Why? Because many of those structures, we don't have enough material available to make those more extensive tests like fatigue tests or tensile tests. And the hardness measurements are much more easy and don't require many available material. So when we have this type of information, we can guarantee structure safety. That's our main motivation. In this research, we did some experiments. The material we use is from this Asian bridge in Brazil that was built between the years of 1864, 1865. It has 173 meters and was built initially only as a railway bridge. But today, because of the high amount of cars that we use, it is also used as a car crossing bridge. And so to compare and have more available data, we also use data from other structures of the same historical period and of course of the same material. So we could have more information about it. Here you can see both profiles on the bridge. So initially we analyzed the chemical position and the microstructure of both profiles, so we could see which material we were dealing with. Then we analyzed we carried out monotonic tensile tests, and for each specimen of this test, we analyzed hardness of each of them. So about the fatigue properties. As I mentioned before, we have some equations with already predefined coefficients. This one is that we call the direct hardness method because we only use the hardness values to obtain fatigue life. That's the only one available. So to have, so we could compare those methods. We also use this one that use the ultimate tensile strength. We call the indirect hardness method. So here we use the hardness data to obtain the ultimate tensile strength. Here you can see equations that provide this relationship. They use different types of hardness, different scales. We compare all of them to see which one provided the best results. As I said, each of them use different scales. So to compare the final results, we converted everything to Vickers hardness so we could see all together. And also, according to this paper and many others, this is the best parameter to estimate, to see if the results are good or not. This value here should be close to 1. Okay, about the results, this is the chemical composition of this material. And here you can see the microstructure of it. It's called Pardal iron, which is really common. This type of structure of this historical period. It's a material with high amount of phosphorus, sulfur, and low content of carbon. The results of the estimation of ultimate tensile for the ultimate tensile strength. You can see that all methods provided similar results, and all of them for values above 150 hardness, Vickers hardness. They are all out of this interval of 10% error here. So to here you can see the E parameter. So to try to have a better estimation, we are proposing this new equation. Here we use the experimental data of the results of the material from this bridge in Brazil, and also from literature. And here you can see that the estimation provided a better result. About the fatigue estimation, on the first method, the direct hardness method, the values of fatigue life were super overestimated. So we removed it here because it was really far from what we expected. But the medians method provided much better results. But again, the estimated results are higher than the experimental ones. So it's not the best method yet. Conclusions and future work. The chemical composition and with the light optical microscope, we could identify the material, which is a Pardal iron, corresponds with the historical period of the construction of this bridge. The correlation between hardness and ultimate tensile strength. The existing equations don't provide a good estimation, so we try to propose a new equation for this type of material, but we should have more data so we could improve this equation. Why I mention this? Because it's really hard to find other papers that provide the hardness measurements, the tensile strength, and fatigue data all together of this type of material. The correlation between hardness and fatigue life, the direct hardness method overestimated, so it's not a good method. The medians method is better, but also provide higher values in the experimental data. And as a future work, we're going probably to work on it, is try to provide a new estimation method for fatigue life for this type of material. Okay, here are the main reference, and that's it.
Thank you.